right, sixth grade, how are we doing today? All right, we are going to start with energy now. So, on page 263 in your book, we are going to start chapter 7, lesson 1, what is energy? We are going to unlock the big questions. How are energy, work, and power related? And what are two types of energy? So, today we are going to answer those questions. And grab a highlighter, grab a pencil, because we are going to read in our books, highlight some information, and answer some questions. We always start out with the My Planet Diary. So let's start out there with some wind farms. Alrighty. So again, start out page 236, wind farms. Did you know that wind can be used to produce electricity? A wind farm is a group of very large windmills or turbines placed in a location to get a lot of wind. The energy of the wind causes the propellers of the wind or of the turbines to spin. The turbines are connected, oh my goodness. The turbines are connected to generators. When the turbines are spinning, the generators produce electricity. The amount of electricity produced depends on the size of the propellers, the number of turbines, and the strength of the wind. I'm going to pause this real quick. Miss Fortunato is calling me. Hold on. I don't know how to pause it. Okay. All right, guys. Sorry. Miss Fortunato needed some Chromebooks. Okay. We just read the My Planet Diary. Let's answer the question. What are some advantages and disadvantages to using wind energy to create electricity? So pause the video, answer that question, and then when you're done, unpause it, and let's move on. How are energy, work, and power related? Did you put a book in your book bag this morning? If so, then did you work on the book? You did work on the book. Recall that work is done when a force moves an object. The ability to do work or cause change is called energy. Highlight the definition for energy. Work and energy. When you do work on an object, some of your energy is transferred to that object. You can think of work as the transfer of energy. When energy is transferred, the object upon which the energy is done gains energy. Highlight that sentence. Energy is measured in joules, the same unit as work. Let's move on. Power and energy. You may recall that power is the rate at which work is done. Since the transfer of energy is work, then power is the rate at which energy is transferred, or the amount of energy transferred in a unit of time. I want you to highlight the bold-faced sentence. And then take your pencil and circle the equation for power. Different machines have different amounts of power. For example, you can use either a hand shovel or a snowblower like the one in figure 1 to remove snow from your driveway. Each transfers the same amount of energy when it moves the snow the same distance. However, you could move the snow faster using a snowblower than a hand shovel. The snowblower has more power because it transfers the same amount of energy to the snow in less time. Let's do the question. It says figure 1, power. The snowblower has more power than the person with the hand shovel. You can use an elevator or stairs to lift a box to the 10th floor. Which has greater power and why? Go ahead and answer that question. And then move on. All right, number number, page 238. Not number, page 238. What are two types of energy? Moving objects, such as the vehicle shown in figure 2, which is down here, have one type of energy. A rock perched on the edge of a cliff or a stretched rubber band have another type of energy. The two basic types of energy are kinetic energy and potential energy. Whether energy is kinetic or potential depends on the motion, position, and shape of the object. I want you to highlight the bold-faced definition. Kinetic energy. A moving object can do work when it strikes another object and moves it. For example, a swinging hammer does work on a nail as it drives the nail into a piece of wood. The hammer has energy because it can do work. The energy an object has due to its motion is called kinetic energy. So an object in motion, or energy of motion, is kinetic energy. Factors affecting kinetic energy. The kinetic energy of an object depends on both its speed and mass. Suppose you are hit with a tennis ball. Hold on, I want you to highlight that. The energy of an object depends on both its speed and its mass. Suppose you are hit with a tennis ball and that has been lightly tossed at you. It probably would not hurt much. What if you were hit with the same tennis ball traveling at a greater speed? It would hurt. The faster an object moves, the more kinetic energy it has. Highlight that sentence. Kinetic energy also increases as mass increases. Suppose a tennis ball rolls across the ground and hits your foot. Compare this to getting hit in the foot with a bowling ball moving at the same speed as the tennis ball. The bowling ball is much more noticeable because it has more kinetic energy than the tennis ball. The bowling ball has more kinetic energy because it has the greater mass. I want you to highlight that kinetic energy also increases as mass increases. I want you to do this over here. So kinetic energy of an object depends on its speed and its mass. Use this diagram over here to complete these two questions. List the vehicles in order of increasing kinetic energy. So think about the speed and the mass. And number 2 says explain another example of two objects that have different kinetic energies. Explain why their kinetic energies are different. If you need to, pause the video. And now let's move on over here. So calculating kinetic energy. You can use the following equation to solve for the kinetic energy of an object. I just want you to highlight the words calculating kinetic energy and then take your pencil and circle the equation. So kinetic energy would equal 1/2 the mass times the speed squared. So for example, suppose a boy is pulling a 10-kilogram wagon at a speed of 1 meter per second. So we would take 1/2 the mass, which is 10 kilograms, times 1 meter per second squared. So it would be 1/2 10, which is 5 kilograms, times 1 meter per second squared, which is just 1. And we would get 5. And we know that we learned in the first page that the label for energy is joules, so it's just 5 joules. And note that 1 kilogram per meter squared per second squared is just 1 joule. So do changes in speed and mass have the same effect on kinetic energy of the wagon? No. Changing the speed of the wagon will have a greater effect on its kinetic energy than changing its mass of the same factor. This is because speed is squared in the kinetic energy equation. For example, doubling the speed of doubling the mass of the wagon will double its kinetic energy. Doubling the speed of the wagon will quadruple its kinetic energy. Turn the page. And now we're going to talk about potential energy. Potential energy. An object does not have to be moving to have energy. Some objects have energy as a result of their shapes or positions. When you lift a book up to your desk from the floor, or compress a spring by winding a toy, you transfer energy to it. The energy you transfer is stored or held in readiness. It might be used later if the book falls or the spring unwinds. Energy that results from position or shape is called potential energy. Highlight that. This type of energy has the potential to do work. Highlight that. Gravitational potential energy. Potential energy related to the object's height is called gravitational potential energy. The gravitational potential energy of an object is equal to the work done to lift it to the height. Remember that work is equal to force multiplied by distance. The force you use to lift an object is equal to its height. The distance you move the object is its height above the ground. You can calculate an object's gravitational potential energy using this equation. Circle the equation. Just the weight times the height. For example, suppose a book has a height of 10 newtons, or a weight of 10 newtons. The book is lifted 2 meters off the ground. The book has 10 newtons times 2 meters, or 20 joules of gravitational potential energy. Figure 3. Rock climbers have gravitational potential energy. Circle the rock climber with the greatest gravitational potential energy. Calculate this potential energy. The height is used by the rock climber. The height to be used is the rock climber's lowest foot. So this one you want to use this foot. This one you want to use this foot, and this foot. And then the last one, where would the rock climber at the top have to climb to have half as much potential energy? And then the last section, elastic potential energy. An object has a different type of potential energy due to its shape. Elastic potential energy is the energy associated with objects that can be compressed or stretched. Highlight that. For example, the girl in figure 4 pressed down on the trampoline changes shape. The trampoline now has potential energy. When the girl pushes off the trampoline, the energy is stored and sends the girl upward. So here we're interpreting the diagram. It says, rank the amount of elastic potential energy of the trampoline from greatest to least. A ranking of 1 is the greatest. Write your answer in the circles, then explain your answer to the space to the right. So you're using 1, 2, and 3 to rank where she has the most elastic potential energy. 2 where it's in the middle, and 3 where she is the least, and then explain it over here. And when you're done with that question, you are done, and you are done with science for the day. So if you're doing this on Friday, I hope you have a great weekend. If you're doing this on Monday, I will see you in class tomorrow. I hope you guys have a great day and enjoy the rest of your day.